As you will soon realize after hearing John's talk and then mine, Colorado is a state with diverse perspectives. The purpose of this forum, which is examining the desirability of the U.S. becoming a methane economy, presupposes the possibility that the gas resources exist to make this a viable choice. Basically, my presentation today is that domestic commercial gas resources are not sufficient to support a natural gas economy. To understand why, let's begin by looking at U.S. gas production just 8 years ago. This is done by type for the contiguous U.S., excluding Alaska, and the three types are conventional gas, basically from good quality reservoirs, transitional gas from generally good quality reservoirs in expensive environments like deep, ultra deep, and deep water, and unconventional gas from poor quality reservoirs. As you can see, production had rebounded from the low in the mid-1980s to reach 19 TCF around 2000 and 2001, primarily because of growing tight sandstone gas and coal bed methane production. But already in the early part of the last decade, mid part of the decade, production dropped to 18 TCF, primarily because conventional production dropped by more than 3 TCF from 2001 to 2006 per year, and that offset growing unconventional production. In fact, the NPC put out a report in early 2007 called Hard Truths about U.S. energy, and one of their hard truths is that we would need, in order to meet demand, we would need to be importing lots of LNG after 2010. Just going forward to see the gas production to 2012, we've had a total turnaround from 18.1 TCF in 2006, we're up to 24.6 TCF, a record level in 2012. 2014, it will definitely exceed 25 TCF. All this increase is due to unconventionals, and to show how that works out, I've divided the unconventionals into tight sandstone and carbonates, coal bed methane, and then shale gas and gas from tight oil formations. You can see huge increase in shale gas and tight gas, and just in those 6 years we went from 1.3 TCF per year to 10.3 TCF per year. Unconventionals as total provided more than 70% of total production by 2012. Conventionals continued to decline. We're down to 6 TCF by 2012. But all those LNG imports we were supposed to need have been totally eliminated. So the proposition that people developed from this is that new technologies have proved their potential. We've created massive amounts of new gas supply. And this increased production occurred despite plummeting prices. In June and July of 2008, wellhead prices exceeded $10 per 1,000 cubic feet. By the spring of 2012, they were below $2, since rebounded to about $4, but still quite low from a historic perspective. And therefore, we've got 100 years or more of gas supply, much of which is going to be low cost. There's a cornucopia of benefits associated with that. We can increase our use of natural gas for transportation, displacing gasoline. We have sufficient gas to displace coal and nuclear for electrical generation, as well as providing a backstop for solar and wind. And we have gas for massive exports. The reality is that we face some major geologic constraints. The majority of new gas areas are low productivity. I appreciate it, Scott showing his slides. Remember all the blue areas? Yes, low productivity areas in these major plays. Costs count. Recent production increases are limited to a few low-cost areas. If you remember Scott's slide on the Marcellus, he shows this bright red area in northeastern Pennsylvania. Basically, in 2011, 2012, and 2013, all the increase in U.S. gas production was coming from that small area, basically about 2 or 3% of the total area of the Marcellus play. Which is another point, is these low-cost areas are geographically limited. They're not widespread. Thus, I would argue that the promise of 100 years of gas supply is in industry terms, and I get about 2 or 3 calls a week from people trying to sell me deals, this is a classic over-promote, a myth, and I mean that in the pejorative sense. It's not helpful to our discussions of what our energy policy should be. I realize that the past slide may sound quite dismissive of the case for 100 years of gas supply. But I think I have to add here that the thinking behind this case does have some respectable intellectual foundations, namely the concept of what's known as the resource pyramid. This concept, which was certainly developed, if not originated, by Professor Stephen Holditch at Texas A&M, asserts in the simplest form that reservoirs vary in quality, from good to poor, and that poor quality reservoirs outnumber good quality reservoirs. Since conventional reservoirs are by definition good quality reservoirs and unconventional reservoirs are poor quality reservoirs, it seems intuitively obvious that unconventional resources should be substantially larger than conventional resources. Professor Holditch developed the concept of the resource pyramid from studies of 22 basins in the United States. As a rough test of this concept, I extended it to all productive basins in the contiguous U.S. and looked at the national resource gas pyramid from 3 different perspectives. The first one, reservoir rock volume. You can see unconventional resources clearly dominate. For purposes of this illustration, I use something like 12 to 1. It could easily be anywhere in the range from 10 to 1 or 15 to 1, and possibly even greater than that. But sheer rock volume is not the most useful standard of comparison. We want to look at porous rock volume, which is the ability of the rock to contain fluids. And most conventional reservoirs have porosity between, say, 16 and 32%. Those would be considered good quality reservoirs. Most unconventional reservoirs, particularly gas shales and tight sandstones, have a porosity of 4 to 8%, only 25% as much. Thus, unconventional reservoirs still dominate when it comes to porous rock volume, but the domination is not as great. It's only 3 to 1. But porous rock volume, which is a good indicator of in-place resources, is, however, not the only indicator of importance. We want to look at recoverable resources in place, which are in-place resources times the recovery rate as our ultimate standard of comparison. Generally, for non-associated gas reservoirs, recovery rates in conventional reservoirs vary between 60 and 90%. For the purposes of the diagram I'm going to show you, unconventional reservoirs, I'll use a recovery rate of 20 to 30%. Scott suggested only 10 to 20% on the major gas shale plays he used. But if we look at it from that perspective, in the perspective of recoverable gas, remember, starting from 12 to 1 in terms of rock volume, we're down to 1-to-1 in terms of recoverable resources. And thus, the shape is no longer a pyramid, but a rectangle, with the two being roughly similar. In other words, much more rock does not necessarily imply much more resource. Where these two differ primarily is in cumulative production. You can see with conventional production, we produced 85% of ultimate recovery. With unconventional gas, we've only produced 20%. Thus, future gas production in the United States will be dominated by unconventional gas. The expression 100 years of gas supply tends to obscure the absolute amount needed to provide that much gas. For the sake of discussion, I will consider 100 years of supply to be 2,500 to 3,000 trillion cubic feet, which is approximately 100 times current consumption of 26 trillion cubic feet, or perhaps a slightly larger amount of consumption. To put this amount in perspective, that would be 2 to 2.5 times the 1,200 TCF we've already produced in the contiguous United States. And it's 4 to 5 times larger than all the gas we produced in the last third of a century, which is when we produced half of what we produced in the cumulative production. 100 years of gas supply thus requires massive gas resources. In conventional resource assessment, we often consider the field size distribution and the number of fields in each size class. Because unconventional accumulations tend to be continuous accumulations, we can't do that. Instead, we have to consider play size distribution in the number of plays in each size class. And just as an intellectual exercise, I developed some play classifications or some subclassifications of mega plays, anything over 30 trillion cubic feet, and major plays, 3 to 30 trillion cubic feet. How many plays would we have to develop of each size to get up to 2,700 trillion cubic feet? There are different ways of doing this as far as getting to the total number, but essentially you have to have a large number of mega plays, these plays over 30 trillion cubic feet. These 19 plays provide over 80% of the total. I want, as a point of comparison, to note that before the development of unconventional gas plays, we only knew of one mega gas play in North America. Instead of considering the requirements for a massive gas supply, this slide focuses on remaining potential, excluding cumulative production, for the number of plays in each size class. You can see that unconventional resources have clearly added to the number of massive gas plays in the United States. Basically, we never even considered mega plays before unconventional plays came on the scene, but the number falls far short of what we need to provide 100 years of gas supply, especially in the mega play category, general category. I'm only saying we have 5 versus a potential of 19. But aren't recent developments in drilling and completion technology creating massive new resources of gas? Yes, they are. But we also need to consider that there are geologic limits on technology that serve to limit the resource amounts. Technology cannot increase low porosity, which are a lot of these blue areas that Scott showed us in these major shale gas plays. If total organic carbon in the source rocks is low, technology can't do anything about that. If it's immature or over-mature, we don't even include it in the play area. If the rocks are high ductility, it makes it very difficult to produce over the long run. We've now advanced completion technology to the point that we could get good initial productivity for a year or two, but in shales with the high clay content, and that's exceeding 35 to 40%, the ability to sustain this production over 5 to 10 years is still a major question mark. And we're also limited in our ability to produce from low pressure formations, especially found in coal bed methane reservoirs. Some of the key lessons we've learned over the past 5 years is that there's high variability within plays. Scott showed this quite dramatically, with differences in well productivity that exceed an order of magnitude. And we have the ability to map, explain, and thus predict this variability. There's the importance of well density and completion practices, which actually seem to apply right now more to tight oil than they do to gas, in that we're really increasing our ability to have more laterals close together in the same section without major interference. Third thing is the importance of the cost of production. As Scott showed some excellent diagrams of what we would consider supply curves relating resource amounts to the cost of production instead of looking at technically recoverable resources. I think in his analysis, he generally showed that those BEG analysis where they calculate technically recoverable, it's at least 1.5 to 2 times economically recoverable at a price up to about $15. So over the past 2 or 3 years, we begin to develop assessment methods that incorporate these lessons, and I'll just quickly go through what the consequences are for the major resource classifications. Shale gas. Basically, what I get here when you subtract cumulative production from ultimate recovery is an outlook of maybe 665 to 1,140 TCF, which at 25 TCF per year is only 27 to 46 years of supply. What that means is that production is likely to plateau by 2020, production greater than 25 TCF per year, likely to be maintained only to 2025 or 2040, and our low-cost gas resources will largely be developed by 2020. In the next decade, we'll need $5 to $8 prices, and in the decades afterwards, we'll need higher prices. That obviously has a lot of implications for demand, but in conclusion, expanded domestic gas resources are not a game changer. They only provide us with a long extra period in a game we are already playing. Thank you.